And Max, how does the audio sound in the room? Can you hear me okay?
Yeah, you can hear you well. And I think we're good to go.
Cool. You think we can get started?
Sure. Yeah.
Okay, so let's kick things off. We have a pretty full agenda today, so let's go ahead and get started now. Welcome to MBONED. If you're in the wrong room, welcome. You might as well stay. It's going to be a good meeting. Here is the note well. You may have seen this before this week. Please take note of this and read it carefully, as it describes contribution and participation and the implications of that. In terms of meeting tips, the usual from the last few meetings, sessions being recorded. And if you need to speak, push the appropriate buttons, add yourself to the queue, unmute yourself. If you'd like to add video, you're welcome to. And of course, masks should be worn within the meeting area. And Max has graciously signed up to be a delegate to enforce this rule with an iron fist, if necessary. So here's the agenda. Agenda bash. Feel free to speak up if we missed anything. We're going to cover the Yang models, AMT Yang models draft, multicast scaling considerations document from Jeffrey. I will be talking about TreeDN draft. We have Ruth and Rich, who will talk about actually a use case and an application of TreeDN that is really exciting and interesting, real world use case of multicast and AMT. Lauren is going to speak, give an update on the multicast menu and some really exciting progress she's made on that to deliver AMT to the browser. And if time allows, we're going to add Mike. Mike will speak to a lessons learned document that looks like it might be more appropriate for PIM, but he'd like to share it. And certainly the folks in this working group are great and ideal for providing feedback on that document. Anyone want to bash or add anything to this agenda? Okay, moving right along. In terms of status of active working groups documents, there's the Yang models draft. Sandy, are you on, and do you have any updates to provide? You're up, Sandy.
Okay. Can you hear me?
Yes.
Okay. This model has been printed several times, and we request a review for many times. We still think if some young doctor or some others can give us more review on it, and we think that it's stable and it's maybe ready for last call. Yeah.
Okay. Thank you. Maybe perhaps Sandy, maybe one last email to the working group requesting review on this document as a reminder, and then whenever you think it's ready for working group last call, why don't you put in again, send to the list and request a working group last call, and we
Okay.
can maybe kick off that process.
Okay, thank you.
Thank you. And to the others in the working group, please. We'd love more feedback. Sandy would love more feedback on that. So just a reminder. The multicast telemetry draft. Greg, Sandy, I believe you guys are both co-authors on that one. Do you have any updates on that?
Sorry, it take me many times to open the mic. So about the redundant ingress failover, we think that it has covered most of the deploy situations. But if some operator or some others who has experience on it, it's better to tell us more about it. And it's great if somebody can review it and give us more suggestion. Yeah.
Okay. Yeah, sorry. That's what I meant. The redundant ingress failover. You guys are co-authors on that. All right. That's another one. Yep, folks, please do take a look, review that doc, be valuable, and provide feedback. Telemetry draft. Let's see. Who is on that? Is Mike McBride in the room? Or any of the co-authors of that one? Hayo,
I think
Mike,
Mike said
Greg.
he'll come. Sorry, just Mike will come when for a slot later, so maybe you can ask him then back again.
Gotcha. Okay. All right. And the multicast to the browser drafts. So back in July, we did a working group last call for the dorms document. At the time, there just wasn't enough responses to advance. I think we only had about 2 or 3 people speak up to support advancing. We need a little bit more than that. So if you would like to see dorms, if you think it is ready to be advanced to IESG, please speak up. In the meantime, unless we don't hear, we're going to have to park it. Separately, the other 3 drafts related to multicast to the browser, AMB, CBAC, and multicast NAT. Jake has kind of let us know that he is now engaged and has been assigned to different projects and no longer has as much time to work on these docs. So he may need so more than likely he is going to need somebody to carry the torch on those drafts. And so if there is anyone interested in proceeding and continuing that work, please do speak up. Let the chairs and Jake know. He would love to have someone pick that up for him, because at this time it looks like he may not be able to devote the appropriate amount of time to get those across the finish line. Any comments or questions on any of these active working group docs? Okay, moving right along. That is all. Okay, let's see. Who is up first? That would be, is it Yishang? Yes, AMT.
Yes.
Let me bring up the slides here. Yisong will now talk about the AMT Yang models draft.
Hello. Hello, everyone. This is Yisong Liu from China Mobile. And today I will introduce the AMT Yang model. This is the first presentation of this draft. And the next slide, please.
Yishang, you should be able to advance this yourself, I think. Try it.
I don't see the button.
Okay, maybe not then. I'll just advance it for you.
So this is the version 0, and then this dropped effort from the operators and vendors, China Mobile, X3C, ZTE, Huawei, and Juniper. Next slide, please. As we know, the AMT defined in the RFC 7450, that the protocol used the UDP-based encapsulation to overcome the situation that the receiver side and between the receiver side and the source side there is no multicast connectivity, means that there is no direct connection. So the AMT enables the sites and hosts or applications that do not have the native multicast access to the network that with the multicast connectivity to the source, and the MT can request and receive the multicast traffic. And there are two main roles in the AMT protocol, and the AMT gateway and the AMT relay. And the AMT gateway can send the request to the relay, and the relay can forward the multicast date through the AMT tunnel. That is the unicast tunnel. So the next slide, please. Okay. I can. Another RFC, the RFC 87777, extends the AMT relay discovery process, and a new DNS resource record is defined to publishing the IP address or a domain name of the AMT relay. And while when the AMT gateway can query the DNS resource record by the source address, and can get the AMT relay address and send the request for the multicast traffic. Based on about two RFCs, we defined the AMT YAM model, and the YAM model augments the routing data model for the control plane protocols. And there are two main parts for the two rows of the AMT protocol, and the AMT relay and the AMT gateway. And for the AMT relay, we define the three parts of that. And the first is that itself parameters, like the address, the tunnel limit, and the secret key timeout. And the second part of the AMT relay is that the AMT tunnels. And we define the gateway address and the gateway port as the key, and also have the multicast flows associated with the specific AMT tunnel. And the third part of the AMT relay is that the DNS resource records, and the parameters defined here reference the RFC 87777 section 4.2. And the second part of this AMT model is that the AMT gateway, and mainly including the pseudo interface and the parameters of the pseudo interface mainly referenced RFC 7450 section 5.2.2. So the next step, we will add some AMT statistics or accounting items in the next version, and we are seeking for more feedback from the working group. That's all. Thank you.
Great, thank you. Any comments, questions, thoughts on this draft? Yishang, are you seeking working group adoption in MBONED?
Yeah, I want to request the working group adoption. Is that I'm very sure, is that appropriate for the version 0?
Is it so? But it is a goal at some point to get it adopted by MBONED. Is that this is the targeted working group you'd like?
Yeah, yeah, yeah. MBONED is the target group. That's absolutely
great. Any other comments for on this AMT Yang draft? Thoughts? Okay. Yishang and co-authors of the draft, you guys might want to post this to the MBONED mailing list and solicit feedback from there.
Yeah, yeah. Thank you.
All right, Jeffrey, you are up. Let me figure out.
All right. So this is informational draft that captures some thoughts from our co-authors listed here on scanning considerations for multicast. Next slide, please. So when we talk about multicast scanning, there are 3 dimensions to think about. And first one is number of receivers, and next one is number of flows, and finally, the size of network. So when it comes to number of receivers, to scale that, we believe that IP multicast is the way to go. It can scale to unlimited number of receivers because the group address there is just a logical representation of all receivers. If the multicast tree grows horizontally and vertically, then you can just reach as many receivers you want. The next one is number of flows. Obviously, the routers have limited capacity to support as many flows that you want. But quite often in a network, many flows, they can be transported by fewer number of tunnels. And that's just like a unicast case. So if you put multicast flow onto tunnels, then where the tunnel is, you don't need those per flows or per multicast tree state anymore. You just need a per tunnel state in some cases. And finally, when you have a large network, and sometimes it's not feasible to use a single tunnel to cover all the that vast network there. You may need to use different tunnels, maybe different types of tunnels in different regions to carry this overlay traffic. Next slide, please. So when it comes to tunneling technologies, traditionally we have IP multicast trees can be used as tunnels. We have MLDP, RSVP, TE, P2MP tunnels, and recently there has been the SR P2MP tunnels, whether it's SR MPOS or SRv6. And there is also ingress replication. With ingress replication, you don't have per tunnel states, but you don't have efficient replication. And beer, on the other hand, gives you efficient replication without requiring per tunnel state. So that's best of all two worlds. And if you want to do traffic engineering and without using per tunnel state, then beer TE gives you that. With beer TE, you have global bit positions that encode replication branches. And there, you may run into some scaling problems when your domain is large. And to fix that, there is the beer RBS, which is, to me, is a basic enhanced beer TE, where you use the local bit positions in the recursive bit string structure. And that allows you to do the traffic engineering per quote unquote tunnel space, but you don't need the per tunnel state. Next slide. When you do tunneling, you need overlay signaling besides the signaling that is needed to set up the tunnels. And the reason is that tunnel ingress need to know which flows to be put on which tunnel. And for certain kind of tunnels, the tunnel ingress also need to know which nodes are the tunnel egresses. For example, ingress replication, RSVP, TE, P2MP tunnel, or even beer tunnel, the ingress need to know where the egresses are. And in some cases, beer egress, tunnel egress is all, they need to join the tunnel. And that's, for example, the MLDP tunnel or IP multicast tunnel. Next slide, please. So when we stick to the overlay signaling, let's say that the traffic that is carried by the tunnel is MLDP traffic or IP multicast traffic, then you can just use the those protocols themselves to signal. For example, if you have MLDP traffic to be carried over other tunnels, then you do MLDP signaling over targeted sessions, and that underneath tunnel could be either P2P or P2MP. You can do beer MLDP over beer, and there is a draft in the beer working group that does that MLDP signaling over beer. Similarly, we can use PIM signaling for IP multicast traffic over other tunnels. Rosen MVPN or PIM MVPN is one example. PIM over beer tunnels is another example. And finally, we also have an option to signal IP multicast over beer using MLD protocol itself. So this is the example of using the same protocol to do the signaling. Next slide, please. And then you can use a different protocol to do the overlay signaling. BGP MVPN is one example. It can be used for IP multicast in the VPN case, and then it can also be used for MLDP VPN multicast, where the MLDP is the PEC protocol. And you can also do global table multicast, whether it's IP or MLDP, but all using BGP signaling. And then Lisp signaling for IP multicast is another example of a different protocol used for overlay signaling for the IP multicast. Next slide, please. So in the BGP MVPN case, we use the PE to PE tunnels to carry the VPN traffic across the core. Those P2P tunnels we refer to as PIMZ tunnels. They are identified by the PIMZ routes. The PIMZ routes binds the overlay flows to underlay tunnels. And those tunnels are instantiated by the underlay tunnel, and the type and instance of the underlay tunnel is encoded in the PTA or PIMZ tunnel attribute of the PIMZ route. End-to-end or a P2P PIMZ tunnel may have different instantiations in different regions for technical, operational, or administrative reasons. Each region could have different types or instances. Here we refer to the regional border routers that is doing different types or different instances of tunnel. We refer to those two as segmentation points. Now, the segmentation points need to maintain overlay states. In this case, it's PIMZ routes. They will stitch the upstream, downstream segments based on the overlay PIMZ routes. Next slide.
2 minutes, Jeffrey.
Yeah, getting there. So the point here is that when you do the segmentation or when you do the tunneling, then those segmentation points or the tunnel ingress egress, they need to maintain overlay states. And that goes back to the original question. When you have many overlay flows, what do you do? How can you scale that? So there are two options here, two ways. One is scale up the segmentation points or tunnel ingress egress so that they can handle that many overlay states. I want to point out one thing here is that multicast forwarding state is not much different from unicast. It's basically a route point to forwarding instructions. Here, the forwarding instruction is basically some replication branches, very similar to the ECMP branches in the unicast case. So if you can scale unicast, you can scale multicast. It's just that your router implementation needs to be prepared to do that. Quite often, a router is optimized to scale for unicast side. They just don't allocate enough resources for multicast. But as long as you design it to scale up, it should be fine. Another way is to scale out. You just put more segmentation points so that each segmentation point only handles some of the overlay flows. Next slide. Summary is that we have existing or in development solutions to scale multicast in all three dimensions at the same time. So I think I can stop here now.
This is Dino. Can you go back to the last slide? When you say to scale up, multicast forwarding state is not much different from unicast. If you're doing head-end replication, or as you refer to it as ingress replication, it is considerably more to store a multicast route than a unicast, because unicast only stores a few next hops equal to what the ECMP fanout would be, usually the number of interfaces on the box. But for head-end replication, you're actually replicating to n number of unicast destinations, which can be really large. And if there's 100, 300 tunnels, it's significantly larger than a unicast entry. I mean, there are advantages and many disadvantages of head-end replication, but the cost is large.
I'll accept that. Thank you.
Shisung is in the queue, so.
Oh, sorry, but I was standing physically in the queue already, so I'm not sure what we do here. So
she actually clicked the button first.
okay, so you don't want my comment now? Not at all. Okay. Excellent.
Yeah, just a reminder, please do jump in the queue. And again, we're a little bit over time, so this will be the last thing, and we'll take everything else to the list, please.
Yeah, very quick question. Actually, thank you for Jeffrey's presentation. I think this is a clear descriptions about the multicast scalability. And maybe you can find similar descriptions in the MSR problem statement. Maybe you have also noticed that. I think we both agree that it is really difficult for one particular solution to can be scalable in all these three dimensions. I really have, can you go back to the maybe first, the slide 2, the previous slide. Only one comment is that the previous, the last, oh, it's okay. Just, I think you mentioned that RBS can be treated as the BRT extension. There is some concern for that point, just because I think it is really different from the existing BR architecture and the forwarding behavior. So maybe we can have more discussions about that point. But I
Sure.
really agree about the scalability
Yeah.
statement. I think this is a good document. Thank you.
Okay, thank you.
Okay, Jeffrey, what are your plans? What are your intentions for this draft? Is it, are you seeking adoption here, PIM, elsewhere?
Originally, I was thinking that this belongs to PIM, and it's indeed just an informational draft. So because I didn't tie this to internet or to MBONED itself, or not to the operations. That's why initially I was thinking about PIM, but we can talk about that.
All right, so we're tight on time, and we squeezed you in at the last minute. So let's, Jeffrey, if you want to bring take things to the list, it'd be great. And again, sorry everybody. We'd love to have more robust conversation and discussion. Apparently, 90 minutes wasn't enough time, so we'll do better next time. And we have a pretty full agenda. So. I am going to talk now about TreeDN. I'm going to try and do this quickly because I discussed this in PIM earlier this morning. And there was lots of robust discussion there. So problem statement is with live audiences kind of exploding. And the great use case is NFL Thursday Night Football. It's American football. They are, for the first time ever, live streaming American football games exclusively, and that began as of 2 months ago. And their first game, Amazon Prime announced that they had over 11 million viewers. So this is, I don't know that we've had that many live simultaneous stream viewers, and if it was one-off events. This is happening now, once a week. So with live audiences exploding to that kind of size, combine that with increasing bit rates, are we approaching an inflection point for network resources consumed by live streaming? If not now, will we ever be? And if the answer to either of those two questions is yes, the next question is, what should we do about it? One thing that a lot of folks, wonder about is, streaming has been around for a long time. People and it's, some would argue it's been saturated already. And some folks might say, what's the difference between, video is video, whether it's on demand or live? If they weren't watching a live stream, they'd be watching an online, movie on Netflix or something like that. What's the difference? There's a key difference with live streaming, and that is the expectation of lower latency. When you have an event like a sporting event, you can't have like a minute or two play out buffer because you run the risk that you may end up getting a text message from a friend about the amazing game-winning score that you haven't seen, or you hear your neighbors or the people at the bar across the street cheering long before you see what happens. And there are other use cases like micro betting, in-game betting, where there's even much tighter requirements for latency. Also, join rates are vastly different. If you look at the network consumption from online streaming, it's pretty predictable, seasonal. Goes up around 8 o'clock, drops down around midnight. It's smooth and predictable. Join rates for live streaming are vastly different. It's more like a step function than a smooth increase. In terms of network-based replication, we've got multicast, and it's been around for a long time, and it's been fairly successful in some places. It's absolutely vital on financial networks, and it's widely used on video distribution networks and VPNs, and some enterprises use it extensively. But internet multicast, not so much. And that's what we're really focused on here is over-the-top use cases, internet multicast, which hasn't enjoyed the same level of success as other deployments. So what went wrong with internet multicast? It's worth looking. If we're going to talk about internet multicast now, we should look at why it hasn't taken over in the last 20-something years. So you can get lots of different opinions as to what's the problem with internet multicast, but I think the three biggest ones are kind of the all or nothing problem, and that is every single layer 3 hop, every router and firewall interface between source and destination must be multicast enabled. If any of those are not, then it's not going to work. That's a pretty significant bar. Things like incremental deployment have not traditionally been available. There's the complaint that multicast is too complex to deploy, operate, and troubleshoot. That operators have long bemoaned. And then there's the chicken and egg problem. There's no audience because there's no multicast audience because there's no multicast content. There's no multicast content because there's no multicast audience. So these are kind of like the biggest issues that have kind of plagued internet multicast. The good news is, and that's what this draft is all about, things have changed. This isn't your grandfather's multicast network. And there are now replication technologies available to address each of these issues. That's what TreeDN leverages. TreeDN is about tree-based CDNs, and it takes advantage of both native and overlay concepts to deliver an end-to-end service, even when parts of the network don't support multicast. So let's start with the native part. That's the on-net. And essentially, native on-net, this is the multicast-enabled part of the network, can leverage SSM. So I don't think I need to tell the folks in this room, but SSM vastly simplifies multicast deployment. It eliminates, I would say 90+% of the complexity of multicast, and it addresses the too complex problem. It gets rid of RPs, MSDP, shared trees, PIM register, NCAP and DCAP, tree switchover, data-driven state creation, all of those things, all of the headaches of multicast are eliminated with SSM. SSM can be realized typically with PIM SSM, but could use any other type of multicast routing protocol from MLDP, GTM, BEER, both control plane or data plane, BGP, MVPN, PDMP, SR, to anything that can realize the SSM service model can be utilized to deliver, to support the native component, the on-net component of multicast. For the parts of the network, however, that are not multicast enabled, this is where overlays come in. And specifically, the most pertinent protocol is AMT, which dynamically builds tunnels from a host to or application to a router that sits at the border of a multicast enabled network. So it could be, a host that is sitting on a unicast only network, a receiver on the unicast only part of the network can dynamically tunnel to the multicast network and receive content. This also simplifies the last mile problem. You can avoid some of the in-home problems like Wi-Fi. And it enables end users to not be so dependent upon their last mile provider. If their last mile provider doesn't support multicast, you can just tunnel right over them and receive the service. So it's really about the service, the multicast service, and building overlays to deliver it. This solves the all or nothing problem, also the chicken and egg problem. And I talk about AMT just because it dynamically builds tunnels and can be deployed in both the application layer, the host, or even a home gateway router. But there are any type of overlay solution like Lisp could be utilized to realize the overlay, to realize this service. Lisp has a nice side effect that, it's more appropriate and effective when you have an off-net source. So you have a source on a unicast-only network that could be one tool that can get that traffic to work. So it's really about incremental deployment. This is something that has traditionally been missing from multicast. Like I said, multicast has usually only been all or nothing, but with TreeDN, it supports that model. So what is TreeDN? Again, it's really nothing new technically. It's just the synthesis of a bunch of things that we've been working on for a long time and understand well. And when you put them together, specifically SSM plus AMT, put them together, that's what TreeDN is. And this is kind of a picture from a 30,000 foot view. You have a multicast source coming from a multicast content provider that is connected to a TreeDN provider, or the MBONE, the multicast enabled part of the internet, which is a subset of the actual internet, can deliver traffic to native receivers, or for off-net receivers can deliver it via AMT relays. Greg, can you wait till the end, or do you have something now?
Oh, no problem. I'll wait to the end.
Just almost there. So diving down into the CDN part of the network. This is what a CDN looks like without multicast, and that is, there's different CDN models, but one of the more common ones is, you have a source that sends traffic to, you deploy a bunch of multicast, CDN boxes. Those are typically, a rack of x86 servers that sit in the network, and you send traffic to one who sends it to the others, and they handle local receivers. That's your CDN without multicast. Here's what CDNs with multicast looks like. Well, first we rename those CDN boxes. We call them AMT relays, and we can push them out to the absolute edge of the multicast-enabled network. The big benefit is if you have edge routers, edge devices that support AMT natively in the forwarding plane, you essentially have a CDN on a chip. You do not need to deploy the cost of a rack of servers that you need to rack and power and plug into routers and consume revenue generating ports on a router. So this is a key benefit of this. So this is a service that can be delivered it should be at a fraction of the cost. Essentially, if you have this infrastructure already in place, it's just a couple lines of configs on your existing devices. So zero capex, arguably zero opex, because there's no space and power, no new space and power and things like that. And then those relays handle local replication. Benefits: more scalably and efficiently utilizes the network. Not just for content today, because I think we fixate sometimes on just the content out there today and how this could be, reduce traffic, but really it makes new content that maybe isn't viable today possible. So think AR live streaming to mass audiences. What if instead of just watching a game, you could feel as if you're sitting in the front row center court, and you can look around and see the celebrities in the crowd and hear what they're saying and have that experience, that immersive experience. And, say that's a 500 meg or a 1 gig stream. Could you deliver that to tens of thousands or hundreds of thousands or millions of simultaneous viewers? I don't know that the internet can handle that today. And if it does, it would be really, really expensive. This essentially makes it, trivial cost to do that. And it allows service providers to offer new services, replication as a service. Send us your multicast content. We will replicate it efficiently, and maybe charge you for the cost of the AMT tunnels. But it should be a fraction the cost of what traditional unicast CDNs experience, because again, it could be wrapped into the existing infrastructure. It's also an open standards-based architecture using widely deployed protocols. Not necessarily a proprietary solution that only works with, say, one CDN. And also, because you're just forwarding packets, there's less coordination required. You're not really storing any data. which sometimes some CDN models do. So you don't have to worry about data storage, protection, key management, relationships between the content provider and the CDN. That's just between the content provider and the end user. The CDN is just forwarding packets. And another nice side benefit is this is a decentralized solution. So it democratizes, it makes it really inexpensive, and thus democratizes content sourcing. You know, is it healthy for the internet that society that only a handful of companies can kind of control all content distribution today? This gets back to the decentralized roots of the internet. Use cases, I focus on, you know, the sexy stuff like video and AR, but really anything that's multi-destination could be. And what's great is Ruth and Rich are about to talk about, you know, another use case of telemetry data that can take advantage of this. But also, maybe less sexy, this is something Jake has talked about for years, is large software file updates, things like OS updates. That's been an issue that's plagued networks for years. All right, so in summary, you know, we could be at a nexus where, you know, supply and demand curves are crossing here. Demand, you know, coming from exploding live audience sizes and increasing bit rates, and supply, we now have, through the work of, you know, this working group and other working groups like PIM, tools out there that make it easier and more available to deploy multicast than ever. And TreeDN is basically a CDN model that is optimized to address this increasing strain that live streaming is putting on networks, to support, you know, content today as well as, you know, new content from new contributors. In terms of next steps, I presented this at MOPS. You know, seeking working group adoption. Either MOPS or MBONED, I think it's a better fit for MOPS. And there, you know, when I presented it on Monday, there seemed to be some support there. So I think we're going to kind of pursue that, but I wanted to share this with this working group. Happy to take questions.
My first in the queue.
Yes, Greg, you're up. Then man, you're up.
But some number of years ago, back when I was at Cisco, I led a group with Torres's help where we prototyped this architecture over WebEx. The additional gains we saw were not just the efficiency of replication distribution, but actually at the content source side, in the number of VMs have to spin up the source content. We saw, I think the numbers were like 90% improvement with only 4 receivers. It was stunning. Additionally, because there was a WebEx product, or intended to be a WebEx product and never went past prototype, we had enterprise receiver networks that were multicast enabled. So we had an AMT coordination at the CE where they could take in an AMT tunnel and then go back to native multicast at their distribution point. Everything we did was successful except getting it past the PMs to actually move the resources into adoption.
Hopefully we can fix it this time. Thanks, Greg. Man.
Yeah, Mankamna, Cisco system. So one question, between AMT relays, do we plan to do some kind of overlay tree building, or it's just keep flooding it?
I wouldn't call it flooding. I would call it just native multicast forwarding.
Okay.
It would just, you could in theory build an overlay, but then, you know, essentially what this technology does is you gain the most benefits where you deploy multicast natively. So those who deploy multicast natively enjoy the best benefits and the most significant benefits, and those who don't get tunneled over. And I'm sorry, we're out of time. Would love to get more feedback. Maybe Stig, if you want to speak while I bring up the other slides for Lauren, but apologies again for not being able to support all the comments in the working group.
Yes, Stig Vinas, just a quick comment. So I like the idea of being more democratic, you know, allowing anyone to send content and so on. But I feel there is more work to be done there, at least documenting how it can be done. And, you know, AMT doesn't support it. Lisp is an option. Are there any solutions that, you know, only require browser support, for instance? Also things like access control, of course, or security aspects.
Sure. And the draft sort of touches on those things, kind of maybe at a high level, hand wavy, but would welcome feedback, in text and thoughts in the draft. So
Yeah, okay, thanks.
great. Thanks. I'm cutting me off now. And Lauren, you're up.
Can I just share my screen? I wanted to be able to demo. If not, I can do it from the
Wait,
browser.
I'm sorry, Lauren, I moved you ahead.
Yeah, I didn't think I was next, but
You are not next. I'm sorry. I got too excited. Rich and Ruth, you are up. Apologies. So Rich and Ruth are going to talk about a deployment that is essentially TreeDN. So that's kind of fitting.
Yes. Hi, good afternoon, everyone. Thanks, Lenny. So my name is Ruth Britton. I'm a computer systems engineer in UMetSat, and together with Rich Adam from Géant, we'll present the UMetCast terrestrial over AMT service. So next slide, please. So just a quick overview of the agenda. I'll just give you a brief introduction to UMetSat, UMetCast terrestrial over AMT service, our testing setup and end use case. And then I'll pass you over to Rich to give an introduction to Géant and the AMT relay setup in the Géant infrastructure. Next slide, please. So just to start, UMetSat is the European Organization for the Exploitation of Meteorological Satellites. So it is the European operational satellite agency for monitoring weather, climate, and the environment from space. It was founded in 1986 as an intergovernmental organization and currently has 30 member states with its headquarters based in Darmstadt in Germany. So UMetSat is responsible for the launch and operation of the satellites, and the subsequent data and products are vital to weather forecasting and make a significant contribution to the monitoring of the environment and climate change. So this data is supplied by us to the national meteorological services of the organization's member and cooperating states in Europe, as well as other users worldwide. Next slide, please.
Ruth, I gave you, you should be able to.
I see. Great, thank you. Okay, perfect. So in order to supply this data to our users, UMetSat has UMetCast, a push service delivering environmental data in near real time to its registered users. So the data delivery is implemented as an IP multicast one-to-many dissemination system with a single transmission from the server and guaranteed timeliness distribution to the end user's reception stations. So therefore, it allows end users to receive the data at their reception station shortly after UMetSat makes it available. The UMetCast platform, seen here, has a single data source where files are encoded into a multicast stream and then transported to the user via two main networks, UMetCast satellite, which is the primary method of dissemination, and UMetCast terrestrial, which is the backup, and this can be done over Géant or over the commercial internet. So we're looking specifically at UMetCast terrestrial today. So for the UMetCast terrestrial over Géant service, the multicast stream will be transferred from the UMetCast platform to the local NREN, in our case DFN, where the service provider picks it up and routes it to the end user, and native multicast is used from the source up to the end user. The majority of the NRENs have enabled native IP multicast support in their network. And for those users who are connected to an NREN which does not support this, we can provide GRE tunnels, but the setup and configuration of this is very, very time consuming and complicated. And then for those without access to an NREN at all, we provide UMetCast terrestrial over the internet. Now, in order to increase our user base, simplify the end user setup, and improve our portfolio of services, we are introducing UMetCast terrestrial over AMT, as highlighted here in red. And this is capable of transporting the multicast streams over NREN or the internet without the reliance on the end-to-end native multicast connectivity. So we can see that currently the UMETcast terrestrial has a lot of potential as a service. It provides a highly available and redundant solution for the dissemination of NRT environmental data. However, while this system has many users globally, we are currently unable to service users in a virtual environment as the internet is not native multicast enabled. And this brings us to our new evolution, which is AMT. So AMT, or automatic multicast tunneling, as was discussed previously, facilitates dynamic multicast connectivity between multicast-enabled networks across islands of unicast-only networks. And the tunneling is performed between AMT relays and AMT gateways using UDP encapsulation and unicast replication. And this allows users to receive data from a multicast source, even in the absence of end-to-end native multicast connectivity. So this diagram here provides a high-level overview of our service. So the multicast streams will be available from one of 3 available AMT relays, which are hosted on the Géant infrastructure. Part of the diagram is actually missing on this slide. I don't know what happened. But Rich will discuss in more detail these relays on the Géant infrastructure. But basically, these each have direct access to the data incoming from the UMETcast platform in UMETSAT. And this is all in place and installed currently. So the client solution is a software-based package, including the AMT gateway functionality and our telecast client application. So looking at a standard user, such as seen here on the diagram, we have Amazon Web Services, Google Cloud, even private or commercial users. They will install the AMT gateway and a telecast client software on their station. The telecast application is our IP multicast software, and it's provided by iDirect, which was formerly ST Engineering. The server runs on the UMETcast platform, ingesting the files, encrypting the contents, and then producing the UMETcast channels using IP multicast. The client software then will receive the multicast streams, decrypt the data, and this will run in conjunction with the AMT gateway software on the end user station. The telecast software also has several recovery mechanisms available, including forward error correction, acknowledgement messages, and negative acknowledgement messages, which ensure that the service is highly available with few lost data packets. The ACNAC functionality is provided to ensure reliable data transfer, and the clients communicate back with the server in UMETSAT via a feedback channel over the internet and not over the AMT tunnels. But the great thing about this is it's entirely software-based. The solution is compatible with any infrastructure, making it very simple and user-friendly setup. So we've tested it on multiple different platforms, first in a dedicated Géant test lab to verify the software, in a standalone Amazon Web Services VM, and finally as part of a bigger project for the European Weather Cloud. And actually that part of the diagram is missing as well. It should be up here in orange. But this is a special case actually. So the European Weather Cloud is a cloud-based collaboration platform for meteorological application development and operations within Europe. So basically this is an ideal solution for when we have multiple UMETcast terrestrial users hosted on the same infrastructure. So basically we set up this AMT replicator VM within the EWC. So this replicator will have the AMT gateway software and the AMT relay software installed and running in parallel on the same VM. So the gateway will connect directly to Géant and request all of the incoming data, and then the relay will be responsible for distributing it internally to the individual users. And this is to ensure that the incoming load onto the platform is reduced so that we have the best and most optimal solution for multiple users on the same environment. So we plan on hosting several software-based AMT relay VMs accessible via a load balancer, each servicing up to 5 AMT gateways. On the EWC, we expect to host up to 20 users, each receiving currently 400 megabit per second, but this is going to increase to 1 gigabit per second over the coming years with our new missions and our new satellites. Here I've left a link to the AMT software, both the gateway and the relay. And this is open source software supported by Juniper Networks as a product of the MBONED working group of the operations and management area of the IETF. So the gateway here is provided in Git. This also has a relay available in this repo as well, except this relay has a memory leak, so it doesn't run for long, and that's why I posted also this second repository provided by the same software developer, and this provides the relay functionality. So we've run multiple tests with this software on several different platforms. One of the main tests we ran was a performance test on the European Weather Cloud. And here we had 3 virtual machines, each with the same specifications, same CPU, same memory, same software running, the AMT gateway and the telecast client. And we tested the file-based availability. So we measured what the client expected to receive versus what they actually received on each of the VMs. And while monitoring this over a few days, we noticed that one virtual machine was losing 10 times more packets than the other 2 VMs, even though from our side, there was no visible difference between the VMs. All of the statistics appeared the same. In addition, we also ran a test with the AMT relay software, and on this particular VM, it started fine, but the performance degraded over time, and eventually it stopped running altogether. So we contacted the EWC cloud provider, and they informed us that this particular VM was on a very, very highly loaded machine. So the software didn't have enough resources to run, and this explained why we were getting these faults in the software. So it was migrated to a different machine, and we noticed a drastic improvement in the availability statistics, and the AMT relay software ran without issues after that. As we expect to have multiple users running this software in cloud environments where they will not necessarily have insight or access to the logs or statistics of the underlying infrastructure, we realized that debugging poor performance on these virtual environments could prove quite challenging. So one parameter is the steal time, which could provide insight into the status of the underlying infrastructure of the VMs. So higher values of a steal time indicate a higher load on the physical machine. And in order to tackle this, then we are using the Elasticsearch monitoring tool in conjunction with MetricBeat, which provides statistics visible on a Kibana GUI for each of the hosts on the EWC. So this will be stalled on all of our client VMs, and alerts will let us know if the steal time exceeds a certain threshold. We also noticed that availability improved when the UDP received packet buffers were increased in the VM, decreasing the number of UDP packet losses that were being reported. And also, in order to provide redundancy to our solution, we have produced a failover script, which monitors the availability of the AMT relays, both software and hardware based. And in the event of one going down, it will automatically connect to the next available relay. As we can see, that has numerous benefits, which are shown here. The solution is carrier independent, meaning the data can be sent over NRENs or the internet, no matter the connectivity. It's entirely software-based solution with a simple and quick setup on the end user station. It is also NAT traversal and firewall friendly, ensuring that it is straightforward to set up and maintain. And most importantly for us, it builds up on existing capabilities and preserves the same interfaces and software vis-a-vis the user as the current UMETcast terrestrial service. So data subscriptions are managed through our Earth observation portal, fully under control of the user. The data integrity is preserved and is sent encrypted through the tunnels, and UMETSAT is fully in control of what data is received by which user. And then to wrap up, for the current status, our throughput and performance testing is complete. We have a client running on the EWC for the past 2 months, receiving 400 megabit per second with this solution, and they have a consistency availability of 99.986%. So this is in line with our other UMETcast terrestrial services. So we have the setup ready in the EWC. We've also tested it in Amazon Web Services. We're already going to offer it to users in the EWC in the next few weeks as a best effort service. We also have ongoing discussions currently with our member states and partners. There's a huge amount of interest in it at the moment, and we also have some pilot users lined up already. And we plan to have the service fully operational by June 2023. And now I'll pass you on to Rich to discuss the Géant setup.
Perfect. Just start this. Thanks very much, Ruth. My laptop's making some pretty interesting noises at the minute, so if it goes a bit wrong, I'll turn the video off. So I won't talk a great deal about us because I'm conscious of time, but we are Géant, and we connect RNE networks across Europe and the world. We also foster collaboration and knowledge sharing communities for RNE members and peers. There's the button for moving the slide. Do you need to enable that for me, Lenny, or are you? Aha! And let's see. We are next one. There we go. Thanks very much. So we have a bunch of members that we do work for, and we are responsible for connecting. Here are some of them. You may or may not work with them. Given the IETF's involvement with RNE networks, I'd be very surprised if you hadn't. These are just some of them. And we also work very closely with the EUMETSAT on a bunch of projects, not least of which AMT is one of them. So what have we been doing? I probably don't need to linger very long on this slide because we've already covered off what AMT is by several people, so that's all good. This is just an example of a data pack that we've captured during our testing across the network, so you can see how it's composed. As you can see, it's pretty simple. There's nothing overly complicated about it. It's merely just a header added in the middle. And what are we using to do the magic? We're using Juniper MX devices, specifically MX204s. We like the 204s. The AMT is in hardware, and we have a vendor-supported contract we can use if we get into trouble. Everything just works, and we can use automation and standard tools, things like Ansible, Jenkins, and robots to do our testing, our provisioning, and our integration testing. The way we build our relays is as a relay on a stick. Essentially, we have a single connection or a single AE connection using LACP out of the MXs, and we connect that to the rest of our network. Why have we done it this way? Well, it's an extremely simple build, very basic protocol configuration. There's very little that can go wrong. And on the redundancy side, as Ruth already talked about, this is done using the client software, and we deploy 3 separate relays so that people can connect to any ones they want. Here is an example of the configuration. Like everything else I've talked about, it's fairly simple. We're not doing anything particularly difficult with it. It's quite easy to enable. All we really need to do is enable the IGMP and the AMT protocol itself. I've left out things like firewalling and PIM because they're not necessarily specific to AMT, but they are in there. Here's some output from our AMT relay. This shows us 2 tunnels that have connected to our relay and have joined several distinct groups that we're then sending traffic over to. Point of note here is that if you notice, the interface that they're bound to is the UD interface. This is using Juniper's standard tunnel services SHA configuration, and it builds dynamic UD interfaces to bind these tunnels to. So again, all standard stuff, all built into the device. We don't really have to do anything special to do that. As Ruth talked about earlier on, we've got 3 relays. Here's a picture of them. It's not terribly complicated, so I won't linger too long on this, but it shows that the relays themselves are using AE bundles, and it also shows that we have them in London, Amsterdam, and Frankfurt. It's not all been fun and games. We've had some caveats and some deployment issues, most of which are now fixed, thankfully. So protocol authentication, by default, there is no protocol authentication on the relay itself. So we've had to get around this by using the Juniper loopback firewall filters. It's not a major drama, but it's just something we need to be aware of if we're provisioning a new firewall to a new router to run the AMT relay. Something to keep in mind and to build into our automation. We also have to enable global IGMP on all of the interfaces on the relay. This is because the the dynamic interfaces, the UV interfaces won't automatically be added into the IGMP protocol as they come up. So we have to enable it on everything so that they are all added in. We tried a bunch of things like specifying templates and various other things, but nothing really did the job. So we enable this globally on the router, and this was probably more than anything else one of the reasons we decided to go for dedicated devices rather than just enabling the protocol on our normal core routers. We also have some MTU restrictions, so the customers or the clients that connect to our relays need to be aware of the MTU size of the traffic that's coming from the stream, and the stream itself should be tailored so that it doesn't go above 470 to account for the AMT header and the encapsulated IP and UDP. What issues have we had? We've had some issues with the packet forwarding engine. In some cases, and we're still not entirely sure the exact trigger points for this. In some cases, the relays wouldn't pass traffic once it had gone through the AMT process. Once it had gone through the protocol, the packet had been created, it would be dropped on egress. This has now been fixed, and it's all good. But certainly, due to the nature of the complexity of this issue, we were super glad to have sort of vendor-supported equipment we could call talented and knowledgeable engineers to get that fixed in a reasonably fast time frame. So that's all good. Originally, when we were looking at this design, we were looking at AMT running on Juniper VMX virtual routers. We did some testing. We did get that up and running in the lab for a little while, but there were some issues with some packet sizes. And as it stands, the full AMT implementation is not supported yet on VMX devices. This is how we've been testing the service. So obviously, Ruth has been testing it using her production ready clients and servers, which has been great. We've also used open source tools like iPerf. Some of the later builds allow you to connect to SSM connections and establish those. Video LAN, also the nightly builds allow you to connect to AMT relays directly without having to use a gateway software or a tunnel, which is nice. We've written some custom code to do some packet sweeps and things like that to make sure that no certain packet sizes get dropped or anything. And we've also integrated this into our continuous integration certifications testing software. This is a suite we use to test new versions of software before we roll it out to production, and we include AMT in that. And I'll give you a little bit more detail on that. And this is an example of what that would look like when it runs and it passes successfully. It sets up a bunch of tests, sets the relay up, sends a bunch of traffic, and then make sure that the packet loss, the response times and things like that are all within specified limits. So all good. That runs 3 or 4 times a night, and we typically run that for a few months on any new version of software we're certifying, so we get a really good flavor for exactly how it performs with that given version of software. Possibly the dullest bar chart you'll see all year, but it is nevertheless accurate. We've been using Expo testers to push a bunch of multicast traffic through this. We can currently run it about a sustained 7.5 gigabits through the router. We suspect that this is due to the configuration of the tunnel services. So we configure tunnel services to reserve up to 10 gigabits of traffic. And so that's we suspect that when we change that, it will increase dramatically, but it's certainly on our roadmap. And speaking of which, looking to the future, we'd like to increase the bandwidth out of these relays to 100 gig. We know that certainly Ruth's team want to push a lot of traffic through our relays, and we want to also potentially offer this to some of the other ends to do their own work on it. So we know that multiples of 10 gig is not going to last us for long. So we need to definitely look into 100 gig and the future from there. Although currently VMXs don't support AMT fully, we do have that on the roadmap. We'd like to see that, and we'll continue working with our vendor to get that pushed through. The idea would be to dynamically spin up those relays in countries where are not necessarily close to our existing hardware relays. So that is something we are very interested in, but right now it's for the future. And also I touched on the fact that the AMT protocol doesn't have built-in authentication. So at the moment, firewall access through to those AMT relays is hard-coded essentially, and every time a non-NREN or non-partner range needs access to it, say for example in Amazon or wherever else, we need to add those networks into that firewall manually. We are looking at other options to get around that, whether it's a software thing or whether we apply some firewalling in front of it. But that's on the roadmap, and I think that's it. Questions? How do I accept those?
Hey, first of all, great stuff. Thanks. I love seeing this torch still burning. I'm curious, have you looked at Jake's work to see if any of that can benefit, and if so, considered integration, maybe taking that torch?
Yeah, so I mean, we used Jake's software quite a lot during our testing phases, certainly the iPerf testing and things like that. So it is something that's in use. It might be, I don't know, Ruth, if it's something you want to touch on. You've been using it a little bit more than I have, I think, and it's probably worth going over.
Yeah, exactly. Jake's been incredibly helpful, actually. We've been in touch with him quite a bit regarding the software and any things that we found with it. And certainly it's been what we're using mainly for our solution. And it's definitely something that we can look into as well in the future. But currently it's working really well for us. So we'll test it with a few users first and see how that goes.
Great. Do you think you have the resources to continue his work in the MBONED? I
think so, yes. At least we hope so. We're definitely trying to definitely, leave some space for that as well.
Okay. Let me know if I could help.
Oh, great. Yeah, no, it's great. No, because we've already spoken to a lot of our users about it, and it's something they're really, really interested in. We want to replace the GRE tunnel setups that we have at the moment completely with AMT. So it's something that, we'll be using a lot in the future.
Great. So I'm getting it taken over the line to standardization, then will be an important part of your success.
Absolutely. Yeah.
Good. Thank you.
Yeah, hi, Max Franke, TU Berlin. I just wanted to ask you, Ruth, what are you using for the relay discovery? Dryad or?
Pardon, can you repeat that?
Sorry, what are you using for the relay discovery?
So the AMT relay is provided again by Jake Holland via his software on GitLab. So the software I left on the slide there. Back a bit.
Is it just Dryad?
Yeah.
Okay.
As far as I know, yeah, absolutely.
Thanks.
Other questions? I'll step in or I'll throw in a question. Ruth, can you talk about what if you didn't use multicast? What if you just did unicast for your terrestrial? Why not just do that? It's easier, more ubiquitous. What kind of savings are you realizing through multicast?
Well, currently we have quite a lot of users that have access to native multicast NRENs, and they're getting very high availability. They have a good setup, and actually a lot of Met offices don't even have the resources really to change their setup. So once they have it going, they tend to stick with it, and just, it works for them. But obviously, not everyone has this possibility. The GRE tunnels in particular are issues for us. They take a really long time to set up. And as well, we also see a lot of problems with them, and it's difficult to troubleshoot. So they're definitely something that we want to completely get rid of, replace entirely by AMT. As well, a lot of users now that we've been talking to, they're all setting up stations in virtual environments. So for new users, we're definitely looking to start them off with AMT because this is such a simple setup. It takes less than half an hour to install and have everything ready for them, which is a huge difference to what they have currently. So for some existing users, native multicast works really well for them. And we have no reason to change this currently, as we have a good setup and we have a contract with Géant for this as well. But for the future, definitely we can look more towards AMT and other solutions as more users go to virtual environments and different setups. But as long as Géant supports native multicast, we'll probably stick with that. Yeah.
Great. Well, thank you, Ruth and Rich. This was really great, and it's kind of a realization of a lot of the work that a lot of folks have been working on over the years. So it's gratifying to see this stuff in action.
Great, thank you.
Okay, so continuing along, there was some mention of multicast to the browser, AMT to the browser. Lauren has been doing some work on this and has been enhancing the multicast menu. So you're up.
Great. Do I have control of the slides?
Lauren, you're very low.
Oops. You will now.
Okay. Great. So yeah, like was mentioned, I was doing some work on improving multicast menu to allow viewing in the browser. If you remember at last IETF, I presented multicast menu as this web application, a central collector of multicast streams that also allowed viewing these streams in VLC. VLC works great, but it was a not terribly friendly process to get it from multicast menu to VLC. I saw something about my mic. I will try to turn it down a little bit. Okay. And then we also demoed off-net sourcing, so live streaming from a phone onto multicast menu and viewing that. Today's improvement that I want to talk about is viewing streams directly in the browser. This is all based on Python AMT gateway that Natalie, Chris, and Eric wrote over the summer. And so what I've done is taken that and integrated it into multicast menu. So from Alice's browser, whoever's browser, there's a GET request sent to multicast menu asking for the viewing page. Multicast menu, upon receiving that, reaches out to the specified AMT relay for whatever stream the user requested, establishes an AMT tunnel. That AMT is sent to a local UDP port. The Python magic that's doing the AMT tunnel establishment sends it to a local UDP port. And then we use FFmpeg all on multicast menu to take that loopback UDP port and turn it into HLS files on the server. Those HLS files are then transmitted back to Alice, back to the user, who plays them with JavaScript in their browser. So it still has the replication component that AMT, that VLC does. It's not true multicast because Alice is presumed to be on a unicast-only network where we have to replicate for that last step. So for a demo, you're welcome to follow along with me on multicast menu, menu.3dn.net. But I'm going to start by doing the same demo that I did at IETF114, where I'm going to start streaming from my iPhone. So I've started to stream on my iPhone. If you go to multicast menu, this is a little hard to demonstrate. Is there any way I can share my screen? Can I request that?
Try requesting.
Okay, I did request. Otherwise, people can view it on their own. The best thing about this is that it is a live thing. All slots for requested media are already taken. Maybe if I stop my video.
Did I grant it?
I'm getting all the slots for requested media. Oh, I need to stop. The slide deck has to be stopped.
Stop the slide deck, yeah.
Okay, so I stopped slides and have a screen request. Yes, okay. Okay, great. So we're on multicast menu. We see that this is my live stream here. We're going to go in and do a little bit of specifying the relay that we're trying to go to. This can be specified automatically later, but so we see that we have, this is the live stream I have going. I'm going to click watch in browser. Speak up if you're not seeing this. It does take a moment the second time, and oftentimes it times out the first time just because it's doing all this work to establish. But after refreshing, we should be able to, so you can hear my voice, you can see the lovely plant in my dorm room. So this is a live stream that I am currently controlling. If I move it around a little bit, the video will eventually catch up. So yeah, so it is live and pretty cool. Going back to slides, which I have here. So I can just finish the slide deck from I'll leave that stream up if anyone wants to join it themselves. But yeah, so that's the demo. We showed viewing a live stream from a phone in a browser. There are a couple things to implement on top of this, kind of a wish list. We talked last time about trending streams and being able to, in multicast menu, track what's being watched the most. This is now much more possible because we can track who's viewing in the browser. The other thing on a more technical note is the teardown between multicast menu and the relay is not great. So this multicast menu doesn't know when no one is interested in watching anymore. So this tunnel stays open indefinitely at this point. Obviously could be improved. And then dynamically handling the AMT relay choice. VLC has this process where it tries all of the AMT relays to see where it gets data. This implementation currently doesn't. It tries the first one, and if that one fails, then it fails. So improving that would be nice. And then making this a little more scalable, looking at kind of web application security type stuff. But yeah, that was a very quick overview. Again, huge thanks to Natalie, Chris, and Eric. Their Python AMT gateway was very helpful in this. And that is my presentation. Let me stop. There we go. Any questions?
This once again pretty awesome stuff. Getting multicast working in a browser is pretty significant. One of the use cases I could envision here is essentially you're moving the replication point from the AMT relay to the actual web server, which might be kind of an interesting use case for things like MEC, edge compute stuff. So that's kind of I think you've stumbled upon a really interesting use case that might scale even way better than AMT could. So this could be a really interesting use case here. Cool. Any other questions for Lauren? Max?
Sorry. Yeah, so have you considered what happens if you deploy the web server actually in the MBONE? So do you always use AMT anyway, or do you first try a native join to get the video natively?
We don't try a native join first simply because it's just deployed in AWS. That's not something that would ever work in the current setup. It would be great to deploy it on the MBONE, again, moving that replication point. I just don't have access to a server there, so.
Max, do I hear you volunteering? providing a web server connected to the MBONE?
I can see about that. So yes, maybe.
Great. Well, again, really awesome stuff. Folks, take a look at, go to treedn.net and check this stuff out. It's going to continue to be enhanced. Really, again, amazing work from Lauren and the other folks with whom she's been collaborating. Cool. So we are sort of out of time. Mike, I had you on the agenda if we had time. If you want to come up and talk about the lessons learned, Doc, until they cut us off, you are welcome.
You know, I'll go ahead and just email the list. I presented in PIM, as you know, so let's go ahead and call it a day. Thanks.
All right, cool. Well, everyone, thank you. Lots of great stuff. I think I learned the lesson that we need to reserve 2 hours, not 90 minutes. So apologies for the rushed agenda, but it's better than having no time at all and us being bored. So thanks, everybody, and we'll see you at IETF 116.
Thanks, everyone.
On the arriving chair.
Oh, yeah.
Was it out early? But then I got to see the demo, so that was good. I really like the